In this video, we're going to introduce our final project, which is applying Bayesian statistics in Geo-tests, which is a very important control experiments conducted in marketing measurements. We're going to start with background introduction, including the definition of Geo-test and how synthetic control is used in Geo-test measurements. In addition, this project is divided into two parts. In the first part, we compared frequentist synthetic control versus Bayesian synthetic control. The main purpose of this part is because the current measurement methods in Geo-test are dominated by frequentist approach. Therefore, we want to explore whether Bayesian approach could outperform frequentist approach from both the point estimate and estimate variance perspectives. In the second part, we applied Bayesian partial pooling or multi-level modeling into multiple Geo-test estimates. So the main reason for this part is due to the noisy nature of the Geo-test data. So that apply Bayesian partial pooling can better handle the heterogeneity information for both within geo uncertainty and between geo variability, which can provide more nuanced inference results and also better predictive performance. And for each part, we're going to introduce methods, data set used at specific part, and also the final results. To understand Geo-tests or Geo-experiments, let's start with A/B test. So A/B tests belong to random controlled trials, which is a standard rule in the industry to estimate causal effects. In A/B tests, random units such as users or customers are randomly assigned into treatment or control groups. And usually only the treatment group will receive an intervention, and the causal effect is measured as the difference between the treatment and control group. This design can help to eliminate selection bias, as any observed difference can be only caused by the intervention itself without the interference of other variables. As for Geo-tests, they are controlled experiments or A/B tests conducted across geographical regions to measure the impact of an intervention, such as a marketing campaign or a policy change. Instead of using users as random units, in Geo-tests, the entire regions are assigned to treatment and control groups, allowing for real-world causal inference while minimizing cross-contamination. You may wonder why use Geo-tests instead of customer-level A/B tests. One reason is that customer-level data is not always available, especially for offline marketing campaign, like a campaign launched in TV. In such cases, Geo-tests can be a good choice because it's easier to assign the test and control group by just shut down the TV campaigns in certain regions. To measure the causal effect or incrementality in Geo-test, a very straightforward approach is to simply calculate the difference between the test or treatment group versus the control group, as shown in the left figure here. However, this approach can be problematic because it does not consider the intrinsic difference between the treatment region and control region in Geo-test. This is actually very common because, for instance, New York is selected as the treatment group and San Francisco is selected as a control group, it is apparent that there are intrinsic difference between these two regions before any interventions. To resolve this issue, scientists have come up with a better approach known as synthetic control, or SC. The main idea of synthetic control is concluded in the right figure here, which is to synthesize a control group that is very similar to the treatment group before the interventions, so that the bias before the interventions can be minimized, and the point estimate at the post-intervention time can be more accurate. Example of how synthetic control is used in Geo-tests is included here, where we have one treatment region A with its matrix data as XA, and we have three control regions including B, C, D with their corresponding matrix data. So for synthetic control, it's simply the weighted sum of the matrix data in the control regions, such that this weighted sum is very close to the data, the matrix data in the treatment region. The specific math to calculate the coefficients, or represent as beta here, for control regions are shown in the right, where these beta coefficients can be solved by minimizing the difference between the data in the treatment region and the beta coefficients multiply the matrix data in the control regions. And both the data in the treatment regions and control regions belong to the pre-intervention time. In addition, there is a constraint for the beta coefficients here, where their sum of the beta coefficients across all control regions should equal to 1, and the coefficient for each control region should be greater than or equal to 0. This constraint actually mimics the real situation, where the contribution of one region in synthetic control should be greater than or equal to 0. And this also improves the interpretability, because the coefficients here represent proportions, making the synthetic control easier to interpret it. For instance, the synthetic control of New York can be represented as 30% from San Francisco and 70% from Boston. In terms of data dimensions, the treatment data X treat pre belongs to dimension of RT, where T represents the time units in the pre-intervention time. And the beta coefficient is in dimension RC, where C represents the number of control regions. Accordingly, the control data in the pre-intervention time belongs to dimension C times T. As for the inference stage, for each time unit in the post-intervention time, the causal effect is calculated as the difference between the data in the treatment region minus the data in the synthetic control, or the weighted sum of the control regions at the same time unit. And accordingly, the cumulative causal effect is calculated as the sum of all the causal effect across all the time units in the post-intervention time. Previously, we introduced frequentist synthetic control, where you can see that it's actually very similar to linear regression, except the constraints in the beta coefficients. And here we proposed a Bayesian synthetic control model referring to this paper here. Specifically, in our Bayesian synthetic control models, In priors, we include sigma, which follows a half normal distribution to ensure it's greater than 0. And also, for the beta coefficients, we let it follows the Dirichlet distribution, which is a very commonly used prior for constrained ways with sum equals to 1 and each way is greater than 0. And for likelihood, we use a parameter called mu to represent the weighted sum of coefficients over the control region data, and then model the data in the treatment region pre to the intervention follows the normal distribution where the min is the synthetic control data or the weighted sum of control data, and the variance is modeled by the sigma in our priors. And the final posterior in our Bayesian synthetic control model follows or is proportional to the likelihood times the priors. And the main advantage for incorporating Bayesian synthetic control modeling here is that it can better quantify the uncertainty of point estimates, and also it can include prior information like the Dirichlet distribution of beta as shown here. And also we think it will be more robust to small sample sizes.
The first part of this project is to compare Bayesian synthetic control versus frequentist synthetic control. And here we use synthetic data, which mimics the situation where a marketing campaign is launched at a treated region during a specific period of time. The main reason we use synthetic data instead of real data here is because the causal effect is known in synthetic data, but usually unknown in real data. Therefore, using synthetic data here is sort of a standard approach to compare different methods in synthetic control so that we can know the ground truth. The synthesized data follows the Gaussian process with periodic kernel to mimic yearly seasonality, which often occurs in real data as shown in this figure here. And the treatment region is marked as Denmark and highlighted in red colors, whereas the 7 control regions are depicted in gray colors in this figure. As for treatment time, it was selected as 2022 January 1st, as shown in the dashed black line here. And the pre-intervention or pre-treatment time has 3 years in weekly frequency, and the post-treatment time has 1 year also in weekly frequency. And the metric here is selected as the sales volume of the marketing campaign in thousands units, and the simulated causal effect or ground truth effect is 0.2, and the cumulative causal effect in this synthesized data during 1 year post-intervention time is 10.4. In Bayesian synthetic control modeling, we used MCMC with knot sampler and 4 chains for 1002 and 1000 draw iterations. The trace plots are shown on the left, where we can see the distribution of each parameter, including the beta coefficients for all 7 regions and the sigma parameter. And also we can see that the 4 traces, their patterns are sort of random without obvious directions. And we've checked that the red for all parameters are very close to 1, suggesting that multiple chains have converged to the same distribution. And in particular, the distribution of parameters in 90% credible interval are shown in the right figure. The reason why we selected 90% credible interval is because the geo-tests are usually very noisy, so that 90% is sort of a standard way to consider the variance of estimates in Bayesian synthetic control method. Here we can see that for beta coefficients, they or have values in the range of 0 to 1. And also the sum of these weights are equal to 1, which satisfy our constraints in Bayesian synthetic control. And also we can check that the sigma distribution is very small and actually matches to the ground truth, where we've set the sigma of or data as 0.1.
Here, we specifically compared the result from frequentist synthetic control and Bayesian synthetic control. The left figure are results from Bayesian modeling. So in the first row, the observation data are represented by the blue dots, and the trend in the pre-intervention time are sort of depicted by the blue color. We can see that first, pre-intervention, the model actually fits very well to the observed data with R-square value of 0.78. This is actually a very good result for Geo-test data. And after the intervention, the result from synthetic control is depicted in orange color, and the observation data is still in the black dots here, and the causal impact is calculated as the difference between the observations and the synthetic control data, and shaded in the blue color here. And we further plot the causal impact out, which is the blue shaded color in the second row, where we can see that before the intervention, the trend kind of fluctuates around 0, suggesting that there's no bias or obvious bias in the Bayesian model fitting before the intervention. And after the intervention, we can see that there's obvious positive causal impact during the post-intervention time. And in the third row, we plotted out the cumulative causal impact during the post-intervention time by summing up all the causal impact along to the time units in the post-intervention time. We can see that it sort of follows a linear trend, which is actually very similar to our ground truth as a linear trend in cumulative causal impact. The results of frequentist synthetic control modeling is shown in the right. So first, we can see that before the intervention, the model fitting is actually not that good to the observation data, with R-square value of only 0.78. And also in the second row for the causal impact figure, we can see that before the intervention, it has this seasonality trend, suggesting that the frequentist modeling actually does not handle the seasonality in our synthetic data very well. And also for the cumulative causal impact figure, we can see that it has this curvature trend, which increases first and decreases second, which also against the ground truth. So overall, we can see that the Bayesian synthetic control fits our data much better than the frequentist one. To better compare the results from frequentist approach versus Bayesian approach, we've overlaid the cumulative causal impact of these two models in the left figure, where the ground truth is plotted in green color, and the Bayesian modeling results are plotted in the orange color, and the result from frequentist approach is depicted using the blue color. So we can clearly see that the result from Bayesian approach matches better to the ground truth with a clear linear trend. In addition, we compared the frequentist model's confidence interval versus the Bayesian model's credible intervals, with the results showing the right. They're all set at the 90% confidence or probability. So we can see that first, for point estimate, it's clear that the point estimate from Bayesian approach is closer to the ground truth, which is highlighted in green color here. And also, the credible interval from Bayesian approach is narrower than the frequentist approach. So overall, we can see that the Bayesian synthetic control method actually outperforms the frequentist approach in our simulated data, which has improved point estimation accuracy, reduced uncertainty, and also better uncertainty quantification by using credible intervals. In the second part, we applied Bayesian multilevel modeling or partial pooling to multiple geo-tests. In our model, in level 1, we assume that the observed estimates theta j hat, or causal effect, is from each geo-test is modeled as a normal distribution of its true effect theta j. For the variance of this normal distribution, the sigma j is null or estimated standard error, reflecting the uncertainty in the measurement for geo-test. And in level 2, for each geo-test, the true effect theta j is assumed to come from a common population distribution which follows the normal distribution with min as mu and variance represented by tau square. And for these hyperpriors, we assume the min mu comes from normal distribution, and the standard deviation tau is modeled as a half Cauchy distribution with beta equals to 1. So the main reason we want to apply Bayesian partial pooling here is because in reality, the geo-test data is usually very noisy, so that the application of Bayesian pooling here can help to improve the point estimate, reduce the variance, and also better handle the heterogeneity information within the geo-test and across geo-tests. For the data set used in Bayesian partial pooling, we've synthesized 20 geo-test data. The main reason why we chose such a small sample size is because geo-tests are usually very expensive to conduct, so that each company can usually conducted limited geo-tests each year. And in terms of the data variations, it's vary across pre-intervention time, post-intervention time, and also true causal effect. So this also mimic the actual situation where the pre-intervention time usually can be set to 1 to 4 years, and the post-intervention time can vary from 1 month to 1 year, and the true causal effect varies between minus 0.3 to 1. We compared the results from unpooled estimates and Bayesian pooled estimates in this figure where the x-axis is the true causal effect and the y-axis is the estimated causal effect. For one point estimate, if it is closer to the diagonal line here, it means it's more accurate. So we can see that the orange point estimates, which come from the Bayesian input results, actually closer to the diagonal line compared with the blue dots representing the output estimates. So we can see that the Bayesian partial pooling actually helps to improve the point estimate accuracy to a certain extent. Here, we further quantified the results for these two approaches by first including the box plot of errors of two approaches in the left figure. So we can see that for the median of the error, the Bayesian pooling results is lower than the unpooled results. And also the distribution of errors in the Bayesian approach is narrower than the unpooled approach. So all these results suggest that the results from Bayesian pooling has been proved with lower errors compared with unpooled approach. And we also include other quantification matrix in evaluation, including bias, MAE, and RMSE. We can see that for all these three matrices, the results from Bayesian pooling approach are slightly better or lower than the unpooled approach. So overall, these results all suggest that the results has been proved in the Bayesian pooling, but we also noticed that the improvement seems to be not very significant, which makes sense given the small sample size we have, and that the unpooled estimates are already very close to the ground truth values. Finally, we compared the credible intervals from Bayesian pooling approach and also the unpooled approach. So here, interestingly, we did not observe obvious narrower of credible intervals from the Bayesian partial pooling approach compared with unpooled approach, but we did observe some shifts as shown here. So overall, we think the Bayesian partial pooling does not improve the estimation variance significantly in our synthetic data compared with the unpooled approach here. To summarize our project, in the first part, we compared Bayesian synthetic control versus the frequentist method. And we found that the Bayesian approach has improved point estimate accuracy, reduced uncertainty, and also better quantification of uncertainty. Considering that the current measurement methods in Geo-tests are dominated by frequentist approach, our result could suggest Bayesian approach as a potentially better or alternative approach compared with the frequentist synthetic control method. In the second part, we applied Bayesian partial pooling or multilevel modeling in multiple Geo-tests and found that it can improve the point estimate accuracy from the unpooled results and also has reduced error. In terms of the credible intervals or confidence intervals, they share similar results based on our synthetic data. And for future works, we can apply both methods to different data sets and also include more experiments of priors to see if the results from both two Bayesian models can be further improved. Finally, as for contribution, as the sole contributor of this project, I'm responsible for all phases, including project design, data synthesis, modeling, analysis, and reporting. And the code of this project is also available as the GitHub link shown here. Thank you for your attention.